I hope you feel excited about participating tonight since there's a few of you. I have lots of questions, and there's not a lot of right or wrong answers, or if there are wrong answers, there's not consequences for them, so don't feel too shy about answering. But I am a faculty in the College of Education at UNL, but I live in the Biomechanics Research Building, and you guys are not from UNO, so I'll tell you, our building is the only research building on UNO's campus. Typically, it's more known for teaching courses when you're faculty there, but we do a lot of research in our building, and I'll talk about a lot of that tonight. But before I get too far into the talk, I want to make sure you know what biomechanics is. So can anyone guess what is biomechanics? Anybody heard of that word before? Yes.
Technology behind motion, like arm movements, etc.
Yeah, that's really good. That's close. So the textbook definition that I know is the study of forces that act on a body and how they produce effects from those forces. But basically, exactly like you said, it uses principles from anatomy and physiology, which is part of biology, and principles from mathematics and physics to apply to human movement so we can understand human movement. So what do you think the first study or species that was studied using biomechanics? A is humans, B, horses, and C, insects. Just guess. Who says A? Raise your hand. B and C? A few say C. So actually it is B. And an interesting thing, the reason that we use biomechanics to study horses wasn't really for an academic purpose, but it was for a bet. So Leland Stanford in 1877 hired someone named Edward Muybridge to prove that there was a time that all four limbs of the horse during a trot are off the ground at the same time. And so he used the biomechanics technology at that time, which was film, to show that. So Leland Stanford won the bet. So we aren't studying horses, but we in this building study human movement. So I'm under health, physical education, and recreation. So we look at different research with human movement, and this is our research team. So we have about 40 to 50 individuals from undergraduate to postdocs and faculty and staff working in the building. And our organizational unit is called the Center for Research in Human Movement Variability, and under that we have 6 different laboratories. I'm going to show you some of them tonight in my examples. But I said our Center is for Research in Human Movement Variability. So what does variability mean? What does that mean to everyone? Variability. Differences in the way people move. And you can get even more specific, and it's differences in one repetition to the next, from one repetition to the next. And this is the focus of research in our building. And variability is actually a good thing. That's something that we believe. So when you're walking on the beach, if you're going to spring break on the beach, and you look at your footprints, and you look back and you are to measure, say, the distance between each of your steps, it won't be the same every time. And we consider that to be good because we can adjust to all the different movement environments that we have to encounter. Maybe icy sidewalks on cold nights like tonight, or moving from grass to sidewalk or something like that. And healthy individuals don't have any difficulties doing that. But elderly individuals, those with movement pathologies, they don't have that capacity, and that's what we study. So one division in our building is called neurophysiology of gait, and we are doing what's called gait analysis. So in this video you can see something moving across the screen, a red arrow coming up. What that is it's a person that has markers on, and the video cameras, which you can can see back here are just recording the position of those markers. Then that arrow that comes up is what's called the ground reaction force vector, and that's basically how the person is pushing against the ground in the front to back, side to side, and up and down directions. And so that's a tool that we use in the gait lab. We have another division that looks at balance and posture. And so just an example, this device up here, we can trick people by manipulating their sensory systems. So we can have them close their eyes, or we move the environment with them so they don't get the sway information that you normally have. Or we can translate the plate so that the somatosensory feedback is altered. And we can study how movement is controlled in that way. We also have robotics and virtual reality rehabilitation and training. So we do work with stroke patients and use virtual reality with different robotics situations. And I'm going to show you an example of that later in the talk. And then we have neuromuscular and sensory systems assessment and rehabilitation. And so we're using different visual stimuli and eye trackers to study how people incorporate all of their sensory systems together to produce movement. So here's a video of our motion capture lab, and it shows this is the front of our building, but just to give you an idea of the type of equipment that we have. So this is our lab. It's about the size of a basketball court. Here we have force platforms in the ground. There's 8 plates, and then there's 2 plates in the treadmill. And up above, those are actually cameras. And the cameras don't take video. They actually just record reflective markers that we put on the people to measure. So where have you seen this type of equipment before? You might not have seen the equipment itself, but you've seen the products of the equipment all over the place. And I'll show you an example here. And this is Motion Analysis Studios. Our cameras are actually from Motion Analysis Corporation. That's a company that makes them. And they're based in Santa Barbara, California. So they're used, this lab is used for all kinds of commercials and TV shows. So you can see the red, those are cameras. So our lab has 16 cameras, which is more than sufficient for the gait analysis we're doing. But they're using, I believe, around 50 cameras. And you're going to see somebody walk through here pretty soon that is outfitted for capture. And he'll have somewhere between 100 and 200 markers on, where we only use 30. And you'll see, once the video keeps going, what the result of this is. So they have a pretty big area. 50 by 50 is probably around this size, but more of a square. And they have a lot of cameras. So here's what's going on in that capture volume. You can see the reflective markers on the individuals in the movie, and you can see all those cameras. And they're doing all kinds of interesting movements here. But once what's happening is those cameras are recording the positions of each of those markers, and basically they're doing animations from real motion to make it more lifelike. So here's what it looks like, what the cameras actually are recording. Then they put that together, and it ends up being like a video game. So that one was from a football video game. And here's the actual, this is a commercial for Madden. So if you watched the movements that the people were doing in the lab, you'll recognize some of them in this commercial. Anybody remember this commercial? It's been a while ago. I think it was maybe Madden 2004. And so some of these, so that motion was from the motion capture. And this technology is actually how they make these commercials and these games and movies so lifelike, because they are actually recording real movement from them, so you can see that. And some other examples of where this type of technology is used: Avatar, Guitar Hero. So they actually had Aerosmith in the studios and had them playing on the guitar and outfitted with all of these markers. So those movements in the video game that the characters do are actually the videos of those, or the movements of those artists. But we don't use it, this technology for video game purposes. We use it to study gait and pathologies. What do I mean by pathology? So elderly individuals who are at risk of falling, patients who have peripheral arterial disease, multiple sclerosis, Parkinson's. And for such pathologies, we develop rehabilitation and evaluate the currently available treatments. So I'm going to go through an example with peripheral arterial disease that has been ongoing in our lab. So first, to tell you what it is, and I'll just call it by PAD, it's a cardiovascular disease where the blockages in the arteries affect the legs rather than the heart. So it's basically the same disease as heart disease, but it affects the legs instead. And it's a really common disease. Up to about 30% of people over the age of 65 have PAD. Some know it and some don't know it. So the risk factors are smoking is the number one, but over the age of 50, you're at a higher risk. Diabetes, high blood pressure, and high blood cholesterol. A lot of times people experience symptoms and they don't do anything about it because they just think they're getting older, when in actuality they have something that's wrong, and they won't go to the doctor until they can't do something really fundamental, like go get their mail or something like that. So the major movement problem in this population is what's called claudication, and that's basically like a cramping or heaviness in the legs that forces these individuals to stop walking after 1 to 3 blocks. Then once they rest, they get more blood flow in their legs and they can start walking again. And why did we start studying this in our lab? It seems kind of strange, but the reason is because the lack of good assessment metrics for the population. So typically what happens is the vascular surgeon or physician will just ask the patient, how much does this problem bother you? What are your symptoms? How far can you walk? They'll measure their blood flow, and they might walk with the patient, but there's no way for them to quantify how severe the disease is. And then from that, they will prescribe either lifestyle changes like risk factor management, diet, exercise, a medication that will help the blood less viscous so it will flow easier, or a special procedure like a bypass surgery or a stenting surgery in the arteries of the legs. So our group is actually the first in the world to try to measure how these patients walk differently from healthy individuals. And so we've been using these assessments, the ones that you saw with the video game, to measure how they walk and then to assess treatments and develop rehabilitation from these measurements. So here's just an example, and this is a movement variability variable to look at how these patients walk differently than healthy people. And so the red bar here is the variability value for a healthy control. And then the blue is a patient with PAD walking before they have any pain. And you can see that it's higher than the control. And then when they're in pain, it gets even higher. So it's interesting that the patients walk differently even before they experience this cramping in their legs, and we can measure that with biomechanics, something that vascular surgeons probably didn't think happened. So why does that happen? Our collaborator, our vascular surgeon, he looks in detail at the muscle of the patients. And so here are 2 muscle biopsies. This is from a healthy person, looks kind of like a steak, right? And this is from a patient with PAD. So a lot of the muscle tissue is atrophied, and if you look really closely, the nuclei in the muscle cells have changed. And if we've measured mitochondrial function, so the mitochondria are kind of like the powerhouse, the energy providers in the cell, and their mitochondria do not function normally. So this is why we see these differences. And one of the main areas of problems for the patients we found in the plantar flexors. Everybody knows the calf muscles, right? And when you're walking, the calf muscles are the primary muscle groups working to help you keep moving forward. Okay, so if those muscles are damaged, that can explain why the patients have difficulty walking, because those muscles aren't working correctly and they're atrophying. So from this finding in our research, we're looking at different technologies that can help them with that. One is just a carbon composite AFO, which is a passive device, but when you put your heel down, that device can kind of capture some of that energy, store it, and then it will recoil when you're pushing off with your toe. And we're measuring that as a way to help these patients walk right now. The other thing, and people always laugh about this, is build an Ironman for their ankle. And that's something that we're working on in our lab, is a powered exoskeleton that goes on the ankle that can be used by patients to help them be more mobile and be more physically active. So we're working right now, the exoskeleton is powered by pneumatics, by basically a big air compressor in the lab, but we will use a different technology to make it portable so they can wear it anywhere. So those are the technologies that we're testing and building right now. Another fun thing that happened in our lab with the motion capture, and you might be interested just because it has Alex Henry in it, who is a kicker from Nebraska who played for the Eagles. So this is a video of him kicking, but he actually came into our lab, and it's going to show our old lab here in a little bit. And this was featured on the Big Ten Network. So there's a mechanical engineering student here at Lincoln who wanted to look at kicking, and they didn't have any kind of lab like ours on campus here at that time. So they came to UNO. So this is our old lab, not our nice new research building. And this is a student, Chase Pfeiffer, who did his thesis through Lincoln, but everything was captured in our lab. So that was kind of a fun day. You can see the cameras. And from the measurements we were taking, we're basically looking at leg motion, velocity, and you can look at velocity at different points along his leg. And we had him come in, a college kicker, and a high school kicker who I think was his younger brother. And we could compare differences between different skill sets. So you can see that's kind of what it looks like. We can measure acceleration and jerk. And so that is a fun thing. So most of the people that work in the lab come from some type of exercise science background. We all love sports, and we would love to just, dork out and do sports-related research. But in the end, we know we need to use our skills to try to help people and help people with movement pathologies have a better quality of life. So I'm going to move from the motion capture lab to robotics. So I was trying to see when the earliest form of robotics found its way into science fiction. And one of the earlier ones I could find was in 1942, a book called Waldo. And there's actually several different books with this character, but a physically disabled man built himself some hands so that he could do some tasks. But this idea didn't just stay in a book. And actually, shortly after this, a Waldo was built to take away radioactive materials in remote locations. So you could obviously use some sort of remote to control the robot so that humans didn't have to be put at risk. And since that time, robotics has been used really heavily. So what are some examples of how we see robotics in our lives? Maybe not directly, but maybe things that you're aware of that robots exist. Pretty soon in cars, right? But
record changers or CD changers.
Yeah, CD changers could be one. A lot in manufacturing, probably. And specifically in movement, there's robotics. So if you're familiar with any kind of rehabilitation like Madonna, they have an exoskeleton, right, that spinal cord injury patients can put on. It goes from the hips down, and it can help them move. And there's different devices like that for movement. And then we also have prosthetic hands that that can be moved as well. So, so here's our robotics laboratory, and the video, I wish I knew how to crop them better. It shows some of the other devices in there, but I'll point out the ones that are important. So this is one of our robotics suites, and over here you can see some laparoscopic tools. This is a different machine, so I'll point it out when it shows again. Just a computer, and we'll get to the tactors here in a little bit. So here you can see the laparoscopic tools, and you can see these portable tactors right here. Okay, so what those are, those connect with a project with robotic laparoscopy. And if you're not familiar with laparoscopic surgery, here's a picture of traditional laparoscopy. And basically, the idea is to make small incisions to do a surgery rather than a big open cut, and that the healing time will be a lot shorter. But the problem is, you can see the surgeon is holding his hands out here, and he has to manipulate these two long devices. So that can make it difficult to do precise surgeries, and also surgeons would be in an awkward position maybe for several hours. So ergonomically, that's not good for the surgeons. So to overcome these limitations, there's something called robotic laparoscopy, and the Da Vinci is the common one that people know, where the surgeon is actually sitting at a console here, and the robot is holding the probes, and then the surgeon is moving them almost like a video game console. Okay, so the question is, how do physicians learn to operate with this robot? I mean, what do you think? Do you just want a medical student to come in and do a surgery on you without what? What do they need? Practice, right? They need practice. So how much practice? Who knows? And about 10 years ago, we started doing this work because there weren't any guidelines for when a medical student or a surgeon was ready to perform surgery. So we actually developed some tasks that students could do with the robot. And so this is a needle passing task, and then the one on the right is a suture tying task. These are common tasks in a surgery, especially this type of surgery. We also had like a cauterizing task and a bimanual carrying task. And we developed a certificate program for surgeons to complete before they would move on to the next level. The one problem with this, though, is it required the students or the surgeons to practice a lot to be able to pass the certificate. But at the Med Center in Omaha, for instance, there's only 2 Da Vinci robots. They cost multiple $1 million a piece, and there's hundreds of medical students. So it's difficult to get practice time on the robots. So the next thing that we did in this project was to develop tasks in virtual reality environments, so that using the tactors that I showed you in the video, we could give them a software to put on the computer. They can check out the tactors, go home and practice. And that's much less expensive than the actual Da Vinci robot. So here you can see the needle passing task in the real environment with the real robotic arms up here, and this is the virtual environment. So it's very similar to them actually doing the task with the robot. So this is the needle passing task, and this is the bimanual carrying task in virtual reality and real life. So even though these tasks aren't perfect, it at least gives surgeons some specific skills that they can master before they move on to the next level of practice. So for the last example that I'm going to give in terms of research is getting lost in a video game. So is anybody familiar with the movie Tron? They remade that recently, and my son just loves it. So the idea is that the person gets lost, the people get lost inside the video game. And we don't really do that in the lab, but the the concept of getting lost is kind of the same thing that we're using in terms of virtual reality. That's the idea, right? That you get so engrossed into something that you feel like you're a part of that environment. And so this is our virtual reality lab. So you can see the 3 screens. We're actually in the process of installing a 180-degree curve screen right now. This device is basically a safety device that is connecting to a harness. So if someone gets really engrossed and falls over, they can get caught by the device. And then the same type of cameras that we have in the gait lab are located here. So that's the virtual reality lab. So when you guys think of virtual reality, how do you think that has been used in our lives, or where have you seen that so far? Virtual reality.
A lot of really
Bad movies, okay.
I use it in my research with older adults.
In what?
I use it in my research.
Okay, in your research.
Maybe like flight simulators.
Okay, yeah, flight simulators. When I think of virtual reality, flight simulators is one. The other is these things. I don't know how well you guys can see that, but I remember them being in the mall when I was like a little kid, or at the rides where it's a roller coaster on the inside and seems really real. And then IMAX, it's supposed to keep you in there. Now in movie theaters, they have those chairs that will move and vibrate and make sounds and things like that to get you into the movies more. But we're using virtual reality for rehabilitation purpose. So here's one of our environments, and this looks like what? You can tell what this is supposed to be? Bowling alley. Not quite. The key is what's on the sides. It's supposed to look like a grocery store. And this is one of our older environments that we had. So this is just the plain one, and it's walking forward and now going backwards. So we can show this environment, have, say, an older person who had an accident and they rehabbed in a center, but we want to get them more into a real life situation in a safe way. We can do that with virtual reality. And then maybe we want to challenge them and do funny things, because when you go to the grocery store, you don't just get to walk straight. There's people there, you have to turn, all kinds of things. So we can challenge them by doing different manipulations with the video. Maybe we can curve it and turn it. And then the last one gets narrow and wider. Even though to you, maybe it doesn't seem challenging, but for an older adult or someone who has had a movement problem, it can be challenging. And to be able to prepare for that situation can be helpful. So this is what our VR system looks like currently. And then the floor is actually, there's a projector on it too, but you can't see that so much in here. We have to have the lights on for the camera. So this is what it looks like. So it's pretty engrossing. And why is virtual reality so important? And a very simple experiment that we did can illustrate that. So you can see here we have the person, and he's got a bunch of stuff taped to his leg. So those are weights. And we put about 10 pounds on one leg. What happens if you walk with 10 pounds on your leg, on one leg? Will it change the way you walk? So how will you walk differently? What do you think?
You're going to lift that leg less.
Okay, so you might limp, right, if your leg is heavier. And that's exactly what happens. So here, the stance time just means how much time the foot is on the ground, okay? And so the red is the leg with the weight. So the person, when they have a weight on their leg, they spend more time with that leg on the ground than the leg without the weights. Situations where this might happen without a weight could be someone who had a stroke, right? They have a unilateral problem, movement problem, and there's all kinds of other situations where this might happen, spinal cord injury, something like that. So why is virtual reality important? In this experiment, this was really old technology. We just had one screen, we weren't very good at programming, so all we have is brick walls and a dirt floor, and it's just providing visual flow. So as they're walking on the treadmill, this picture just looks like it's going forward. Kind of like in Mario Kart, you know, in Bowser's Castle, you're driving, it just looked like that, like you're driving. But we turned that on, and the weight is still on. This is what happens. So just by using one simple visual flow, we took away the limp. They still have the weight on their leg. So that's amazing. Just by turning on a simple virtual reality environment, we can take away an asymmetry. So maybe we can do this for amputees, for patients with stroke, for patients with spinal cord injury, just by using a visual stimulus. We trick the body, we trick the somatosensory system into saying your legs have even weight. You walk symmetrically, just with vision. Okay, so that shows how powerful virtual reality can be as a rehabilitation tool. And so we've been using this paradigm in all kinds of different situations. And we just finished a grant that was funded by NASA for this reason, because astronauts, they get all messed up in terms of their sensory motor systems, because in space we don't have gravity. So the vestibular system, which is dependent on gravity, is really affected. And so we're trying to find ways that will help astronauts adapt more quickly when they come back to Earth. And so we use virtual reality, and we use tactors, which give little vibrations at the bottom of the feet, to try and do this. So my team went down to Johnson Space Center, and we did experiments there. So this student actually did her undergraduate in our lab, and her master's degree in our lab, and then she works for Johnson Space Center. So that's how we connected on the grant. And this is a special treadmill we use there, and it's called a 6 degree of freedom treadmill. So it's basically a treadmill put on top of a ball. So it will move based on where the people step. And so if you can imagine, that's a difficult environment to work with. And so we use virtual reality and these tactors to try and help people adapt to that environment. So with that, I want to thank you and give you some time for questions. I hope I gave you some examples of different technologies that were used and how we're using them in different pathological populations. So thank you very much.